Welcome to this next session on data structures and algorithms. In this session, we will discuss the notions of big O, basically continuing on big O from the previous lecture, introduce new concepts such as that of omega, theta and small o. In addition, we will also provide an useful framework for analyzing recurrence equations. So recall our formalization of the first notion of rate of growth. We tried and bounded the rate of growth of a function based on something called the big O, and it says that the upper bound for Tn is c times f of n for all values of n greater than or equal to n naught. So asymptotically the function is bounded, Tn is bounded by some other function fn. We also explained the benefit of the c. C makes it possible to ignore the multiplicative constants that may be associated with fn. On the other hand, n naught helps ignore additive constants that may be a part of Tn. So the idea is to focus only on the dominating term, which is n. So let us understand this growth with an example. So we claim that a particular function fn, defined here as 5 into n plus 6, is order of gn, where gn is defined to be n. So what are we saying? That we are saying fn, which is 5n plus 6, is order n, which means for all n greater than or equal to n naught, fn is upper bounded by some constant c times gn. So let us understand with this illustration. So we find that the pink line fn is indeed bounded not by gn itself, but a scaled version of gn, which is 7 times gn. So you could think of c as 7 and therefore conclude that fn is order of n, 5n plus 1 is order of n. This happens for some value of n naught, which is somewhere between 2 and 4. So certainly for all n greater than or equal to 4 you have this inequality. How about some other interesting functions? How about gn itself? Now we find that gn is always below fn. Can we define something more interesting between fn and gn? It appears that fn is sandwiched between gn and a scale version of gn. So this is basically 7 times gn, and the curve here is basically gn, and here is fn. It turns out that one can formally define something called theta and omega. So omega is basically stating a lower bound, just like big O gives you an upper bound. One can say that fn equals omega gn, that is for all n greater than or equal to n naught, fn is less than or equal to some c prime times gn. Here the c prime happens to be 1. So let me rewrite this. This is indeed c prime equals 1, and this corresponds to 1 times gn, a small mistake in my inequality. Fn is lower bounded by c prime times gn. and the fact that Fn is OGN and omega Gn sandwiched between two versions of Gn prompts another definition called theta. So Fn is theta of Gn if Fn is OGN and Fn is also omega Gn. One could also draw some very other interesting conclusions from this graph. The fact that Fn has been lower bounded by Gn with a scale value of 7 should also give you a hint that Gn appears to be lower bounded by Fn for some value of C prime. So in fact one can say that Gn equals omega Fn with C prime value of 1 by 7, exactly the reciprocal of what was used here. On similar terms, one could talk of Gn being theta f of n. This is based on the fact that Gn is omega Fn, and you could also conclude that Gn is O of Fn. Well, what implies that Gn is O of Fn? Gn is O of Fn with C prime equals 1 or C equals 1 if you want to be consistent with O. So Gn is O of Fn, Gn is omega Fn, that gives us Gn is theta Fn. So let us formalize these other definitions. So Tn is omega Fn if there are positive constants C and n naught such that Tn greater than or equal to C of Fn whenever n greater than or equal to n naught. So it is just that now we have found a lower bound beyond an n naught. So it is an asymptotic lower bound, or the growth rate of Tn is asymptotically more than that of Gn. Tn is theta Fn if they have similar growth rates, that is growth rate of Tn and Fn are the same. Now we can also define a small o of Fn. So Tn is small o Fn if for all positive constants C there is an n naught such that Tn is strictly less than small c times Fn when n is greater than n. That is the growth rate of Tn is strictly less than that of Fn. So you could think of specific instance of big O. So if Tn equals small o of Fn, you can conclude that Tn is also big O of Fn. Now what is really the difference between small o and big O? Well, if Tn is big O of Fn, it may still be theta Fn if Tn also happens to be omega Fn. But this is not true with small o. If Tn is small o Fn, it will not be theta Fn. There is no way that Fn gives you a tight bound for Tn, because even if Tn had omega Fn, you do not get, in fact you get a contradiction. So let us give some examples to illustrate what we just discussed. 2n plus 3 can be shown to be order n. Now it is possible to choose a value of n naught and a corresponding value of 6 as C such that Tn is less than Cfn, that is 2n plus 3 is less than 6n for all n greater than or equal to 1. Now there is no unique combination of C and n naught, but all you are interested in is existence. Now one might wonder, is there a unique function Fn which gives you big O for a given function t? No. So it turns out that Tn plus 3 is also On square, it is also On cube. In fact, it is On raised to k for k greater than or equal to 1 actually. But what we are interested in general is the tightest or lowest order. So note that O was basically an upper bound. So while you can get arbitrary upper bounds, in fact upper bounds for the function that is basically big O for a function Tn are also upper bounds. So if Tn is big O of Fn and Fn in turn is big O of Gn, then you can show that Tn will also be big O of Gn and so on. But what we want is the tightest upper bound. We want to go as much close to Tn as possible. So generally by big O Fn for Tn, we mean the tightest upper bound. So going back to the example, you actually can show that you can't get better than order n for 2n plus 3. So Tn is actually order n, and in fact Tn is theta Fn, where Fn is given by n. So in which case the other higher order terms actually become meaningless. The other point to note is you might have lots of trailing terms. So 4n square plus n plus 5. Now you can show that this is nothing but order n square. It is also order n square plus n. Again, order n square is order n square plus n. So n square is order n square plus n, and therefore all these higher orders will also be order for 4n square plus n plus 5. But as before, we are interested in the tightest upper bound, and one more hint towards getting to this is to ignore lower order terms. So you typically ignore these lower order terms. Well, of course you are interested in the lower order terms for the original function, but not while stating the order. So thus phi n plus 3 log n is order n, because log n is also order n. So we do not formally prove finding of C and n naught, that is the general convention. You just write the order intuitively based on the dominating term. And I will again point out that for this particular example 4n square was the dominating term, or phi n was the dominating term. So here is an exercise for you. Try and build an alternative search algorithm, and we call it interpolation search. Now imagine that you were trying to find an element in a sequence S, but a large sequence S, and imagine that you had the sequence S written across hard disks. So let us say this part of the sequence S was written on hard disk 1, other part was written in disk 2. So remember that binary search required you to find a mid element. Now how do you find a mid element? Even an array, for an array that gets sorted across the disk, you might have that the high element is here and the low element is in the subarray on the other disk. So the idea is, instead of looking for mid all the time, you can sometimes look for the next element. The call for the next element, this should be remind you of linear scan. So what we are doing here is interpolating between linear scan search, which was an order n, and binary search, which was order of log n. Now again, when is this practical? Well, it makes sense only if every access is very expensive. So retrieving this array from disk 1 and then retrieving the array from disk 2 and then going back to disk 1 and so on is expensive, holding it in memory can be expensive. So therefore each comparison might require disk access. The other requirement is that data must not only be sorted, it must be fairly uniformly distributed. What you do not want is a sequence like 1, 2, 4, 8, 16. Sequence scan will, binary search may not be productive. So a phone book is fairly uniformly distributed. So for example, if the input items are 1, 2, 4, 8, the distribution is not uniform. So you can try out the exercise of analyzing such an interpolation search. And to begin with, you might want to formulate the interpolation search algorithm and then analyze it. We are going to next discuss a very important theorem that we could make use of to prove several recurrence relations. As we will see, several algorithms such as divide and conquer have recursions, they are recursive in nature, and therefore recurrence relations become very natural in expressing the time complexity. So what does this mean? This means that Tn is T of n by a plus T of 1 minus 1 by a times n plus something something and so on. How do you solve such general recurrence relations? It is enough to give some asymptotic characterization for associating the cost of an algorithm. So we might not be interested in Tn for very small values of n, as long as we are able to characterize both the recurrence relation and its solution for n greater than or equal to n naught. For all n greater than or equal to n naught, we are fine. So the master theorem gives such a tool for solving recurrence relations in the asymptotic case. More specifically, if Tn is of the form a times Tn by b plus Fn, where a and b are constants greater than or equal to 1 and Fn is a function, you could invoke the master theorem to solve. For more details of the master theorem, you could look at section 4.5 of the third edition of CLRS. So what is the master theorem? So let us say Tn is a times Tn by b plus Fn. Now this n by b here could be replaced with either the floor or its ceiling, and master theorem provides the following asymptotic bounds for Tn. So it is all based on cases, and there are 3 cases. If Fn is big O, and I repeat, we are looking at an upper bound for Fn which looks like n raised to log to the base b of a minus epsilon. This has something to do with the structure of the problem that is invoked to prove the master theorem, but many cases this just turns out to be something like square or cube. So n raised to 2 is a very classic example. However, you need a small epsilon which is non-zero. In such a case, you can say that Tn is theta n raised to log to the base b of a. Another example or another case is when Fn is big O of n raised to log to the base b of a, but there is no epsilon, the epsilon is missing. It turns out that Tn continues to have a theta component with n raised to log to the base b of a, but there is also an additional log n. So this is a kind of price that you are paying for not being able to prove strict better lower bound that we had in case 1. A third case is when you actually have a lower bound for Fn with a plus epsilon. You are not even able to prove lower bound with n raised to log to the base b of a, you need this epsilon shift. Additionally, if f of n by b times a is less than or equal to c of Fn for some constant c and for all sufficiently large n, then Tn is theta of Fn. So now what did we find? We are basically saying that Fn started dominating in the third case. In the second case, and in fact even in the first case, we somehow were able to get Fn on par with Tn, but in the third case the Fn actually just dominates. The recurrence relation yields to a large value of Fn. So the intuition here is basically to compare function Fn with n raised to log to the base b of a. Larger of the two determines the solution. The case 3 is where Fn was really large. So case 1 is if the function is larger than Fn, case 2 is Fn and n2 log to the base b of a are of similar size, case 3 is when the function Fn is dominating. And here are some examples. So Tn is 9 times T of n by 3, here A is 9 and B is 3. There is also Fn which is n. So for suitable values of A and B, for these values of A and B, and for a suitable epsilon, we can show that n raised to log to the base b of A is actually theta n square. So log to the base b of A is nothing but square is 2, so this is n square minus epsilon, and this is basically theta n square. So since Fn is big O of n raised to log to the base 3 of 9 where epsilon is 1, we can apply case 1 to find that Tn is theta n square. So what we have here is n raised to log to the base b of A actually dominates. We can also consider another example, a different case here. This involves case 2, the previous was case 1. So case 2 is about Fn and T of n b and n raised to the log to the base b of A being comparable, and the log to the base b of A is log to the base 5 by 3 of 1. Now you can again find out Fn, and Fn turns out to be theta of 1. This is basically can be shown to be theta constant 1, in which case you can actually apply the second case, Tn is theta log n. So remember we have this additional log n component, and we will have the n raised to log to the base b of A, which turns out to be just theta 1. A third example is when we have an omega lower bound for Fn. So Fn actually starts dominating. So A is 3, B is 4, so B, the base for the log, is actually larger than A. So you can show that n raised to log to the base b of A is order of n raised to 0.793, and this basically shows that Fn is omega times n raised to 0.793 plus epsilon. Now this epsilon is whatever needs to be computed, the remaining component, this is 1 minus 0.793, and you can easily show that this leads to the case 3, which basically gives you a theta n log n tight bound. There are several cases where you can't even invoke Master's theorem. So for example, if Tn is cos n, not very clear how we could invoke Master's theorem, because the fundamental problem is Tn is not even monotone. You could also look at other exponentiated forms of Fn. So Fn could be 3 raised to n. It is not even polynomial, because remember that we were comparing Fn with n raised to the log to the base b of A, where A and B are expected to be constants. So you are not able to deal with cases where n sits in the exponent. So we are in general interested in polynomial fn's as far as master theorem is concerned. Now, well, you might have a polynomial, Tn is under root n square plus 3, but then b is not a constant. Again, you can have a case where a is not a constant. It all boils down to writing down these expressions here and identifying possible exponents for n, but in neither case you will find n of the form n raised to log base b of a for constant a or constant b. And finally, here is an interesting case where fn is not even positive, and well, that isn't a case that master theorem can handle. Thank you.